Okay, we'll get started. So last time we started just introducing this idea of transient response. Does everybody at least know why we're doing this transient response thing? I mean, the objective is to, see how fast or how much time these capacitors and inductors, which are energy storage elements, charge or discharge. I mean, we saw that for resistors, you put a voltage across the resistor, instantaneously you will have a current, right? But the voltage and current relationships across capacitors and inductors and through them have a time dependence, right? So the capacitor current was equal to what? C dVc by dt. The capacitor current was equal to the capacitance multiplied by the time variation of voltage across the capacitance. And inductor voltage was the same. VL, or inductor voltage, was equal to LdI by dt, time variation of current through the inductor, right? So capacitors and inductors have terminal characteristics, meaning voltages and currents, that are time dependent. In resistors don't, right? So because of this time dependence phenomena, then there is a transient response associated with using these elements, like a battery concept, like the train concept that we talked about. The education city trains will have these large capacitors on them. They come into the station, they will charge the capacitors. So they need to stay at the station for a certain period of time. And then they can go from station to station. And this is using the energy that's stored in the capacitance. The energy is half CV squared. So this energy stored in the capacitance, by the time they reach the next stop, that energy would have dissipated to some extent. Energy is half CV squared. C is not going to change. So what changed? The voltage across the capacitance. So what happened was charge, instead of charge being deposited on the capacitor, charge was drawn from the capacitor. Charge moving is current, right? So current was drawn from the capacitor because it was connected to a load. And this happened for a certain period of time. So what is the final voltage of the capacitor, right? Things like this is what we need to answer. It also helps when you're talking about power conditioning circuits. If you want to change a voltage from one level to another, you use lots of inductors and capacitors to do that. So you charge a capacitor to a certain voltage, charge a second capacitor to a certain voltage, for example. So now you have two capacitors. So maybe you can double the voltage at the output by putting these two capacitors in series, right? So people in electrical engineering have developed circuits to do that. Charge this, charge that, put them in series, and I have double the voltage. Charge this, charge that, put them in parallel, and I can double the current at the same voltage, right? But we have to know how fast. Okay, how fast can I do this rearrangement of the circuit, right? So all of that is the motivation behind this chapter here. So we talked about this simple circuit, and we'll talk more about it in more detail. So again, we said it's all motivated by the fact that the relationships between voltages and currents across and through capacitors and inductors have a time dependence, right? These are the major relationships that we have across the three elements that we have, R's, C's, and L's, and this has no time dependence at all. This has a time dependence. These two have time dependence. The voltage across an inductor and the current through it, and the voltage and current through and across a capacitor. Okay? And again, continuously think of the analogy, right? The analogy for the inductor is this water wheel. There's time associated with this water wheel, filling up with water so they can create a smooth flow rate. Same thing with the capacitance, this diaphragm that's at the bottom of the channel. You need to fill that diaphragm, which takes time, and at that point the pressure changes, which is corresponding to the voltage across the capacitor, right? So if you think of the analogy, things will look good. You will help you really understand what we're talking about. Of course, if we have a circuit with a water wheel and a diaphragm, right? Then the circuit has two time-dependent components. Two components with time dependence of voltages and current. So maybe the water wheel will have to go to steady state first, and then you will be able to fill that channel and increase the voltage across the pressure across the diaphragm, right? So the more elements you have in the system that are time dependent or have a time variation of voltage and current across them and through them, then the higher the order of the system that you're building. Right? If you have a system, a fluid system with these two time varying components, then it's a second order system. You have one of the state. You take control in chemical engineering? Control? Dr. Muhammad Nunu, I'm sure. Huh? Next year? So you will study this more in control. So in control, what you want to do is you want to study the time domain behavior of your process, right? So if all you do is, if you have a pipe, if you have just a pipe that you're pushing fluid from one side, getting from the other side, there's no time delay. You put fluid, you will get fluid, right? Assuming it was filled initially, okay? Put fluid, you get fluid. But what if you have a water wheel in there? Then there is a time dependence of the flow in the output, right? So that's where your process control comes in. You will have to design your process controller to maybe initially push more fluid so that you can ramp up the output flow rate quickly and then bring it down so that you can maintain a constant flow rate at a certain value, right? So that is one time varying element. And in control, we call that a state variable. It's a variable, it's a state variable that your system will be defined by. And then if you have this other diaphragm as well in the circuit that you need to run this water wheel at a steady flow rate so that you can increase the pressure in this diaphragm, then that's another sort of time constant that your circuit has to deal with. So in this case, the circuit has two state variables, and to be a second order system, right? We will only deal with first order systems. We will only dealing with circuits with R's and C's or circuits with R's and L's. Okay? If you have R's and C's together, R's and L's together, it's a second order system. And you have to solve it using a second order differential equation. And I don't like math, so I just like to approximate everything with first order. So, but I'm sure you've taken differential equations and solved first order and second order differential equations, right? So we will only limit ourselves to first order differential equation. And this is where this comes from. The fact that we only have one C or one L or one energy storage element in the circuit. And the solution of the RC, these first order systems is very similar. Whether you use an RL or RC, the solution is very similar. So we'll figure out how to generalize the solution for a first order system, and then we will look at RC circuits and RL circuits, and we will just substitute, and we'll find it very easy to find out what the value of voltage across the capacitor is or value of current through an inductor is. That's the objective of this chapter. So in a circuit like this, like we have here, they trying to show you that the response is a first order differential equation. So what they did was, you can do two things. You can either do Kirchhoff current law or Kirchhoff voltage law. So what they did here was do Kirchhoff current law, Kirchhoff voltage law around the loop. So going from this node, they went around the loop, and they saw that we went from the Vs from minus to positive, so it's minus Vs, and then current was flowing. They assume current is flowing in this direction because they define the polarity of the voltage across the capacitor. The capacitor is a passive element, right? If you define the polarity this way, that means current is flowing from the positive to the negative terminal, right? Since it's a passive element. Right, so we define the polarity, the direction of current flowing this way. So I can put a positive here and negative here for the capacitor. That they've defined that for you. They put it, which means also that the current is flowing this way in the resistor. So I put positive here and negative here. Right? So now apply Kirchhoff voltage law. Anytime you see an element, take it into consideration in the capacitor. So the sum of voltages around the loop will be 0. I'm starting with this node, and I have to go back to this node. First, I see the Vs. I see first the negative terminal and the positive terminal, so it's a minus Vs. Then I see the resistor. So the voltage across the resistor is equal to R times I. I is the current flowing through it. And I first see the positive sign, then the negative sign, right? So it's a plus R times I, right? Then I see the capacitor. I see the plus terminal, then the negative terminal. So it's plus Vc equal to 0. And then I know that the current through the capacitor is equal to C dVc by dt. This is from the capacitor's physics, right? So I can substitute C dVc by dt in the above equation. So I end up with, minus Vs plus Rc dVc by dt plus Vc of t equal to 0, right? Or I can rewrite this down to that I can divide by Rc, just because it's going to be interesting for us to have Rc together, and I'll explain why later. If I divide it up, then I end up with a first order differential equation, because the highest derivative is 1. All the terms are linear, so here the term is 1, the term is 1 over Rc, the term here is Vs over Rc, so there's no x times y, there's no nonlinear terms here. I'm not multiplying voltage by current, for example. So two time varying phenomena, I'm not multiplying them by each other. It's either a constant or a constant multiplied by a time varying element, right? So there's no two time varying elements multiplied by each other. So, and it's also non-homogeneous, meaning the right hand side has a value. So if we bring the constant to the right hand side, which is Vs over Rc, then this right hand side has a value. If this right hand side is 0, it's called a homogeneous equation, right? If you just refresh your first order differential equation map. So we're claiming that any RC circuit or RL circuit can be described by a relation that looks very similar to this. And we will do both RL and this is an RC circuit. How about if I don't have a source? Vs is 0, then this right hand side is 0, right? It doesn't affect the left hand side, right? So in this case, it would be a homogeneous equation, right? So we will deal with both cases here, because the case where the train is in motion, right? We charge it and we charge the capacitor to a certain voltage, and the train now needs to move to the next station. There's no source. There's no external source. The capacitor, in this case, is discharging to the load. There's no Vs. This case is the train is stopping at a station. The source is there, and I'm charging the capacitor. Right? After you move, the source is not there. There is a load, another load that's connected here, that is representing the motion of the train. It's a load that's dissipating power, right? So this capacitor in that case will be discharging through that load. The equation, the governing equation, will be the same, except that this will be 0, right? We're okay with this? The Vs will be 0, and the R will be, instead of one R, there will be these two R's in series. Okay? So this is the general format of the equation. So if we have, so now just a review, a math review I think is the next one, how to solve these first order differential equations generally, is what we'll do next. So no, before that, we'll show you that the same thing happens for the RL circuit. So for the RL circuit, we do the same thing, right? So we assume current flowing in this direction, then we have the positive sign for the resistor here, negative sign here, Kirchhoff voltage law around the loop, minus Vs plus this voltage is equal to 0. Voltage across an inductor is equal to LdI by dt. Substitute that here, and you end up with a first order differential equation. Bring the constants on one side, so I end up with this. So the format of the equation looks the same, just a different parameter. The format is the same. Same thing, if I don't have a source, this right hand side is 0. It becomes a homogeneous equation. Okay, so we agree that the format, the solution will be very similar. If we now go and review how do we solve an equation, how do we solve a first order differential equation that with or without a source, or with or without a homogeneous or non-homogeneous equation. So that's the objective of what we're going to do next. And then when we have the generalized solution, we will just substitute with the parameters that we have here for in each of the equations. So in one of the equations for the RC circuit, the parameter in front of the differential is 1. The parameter in front of to solve for the current, the parameter that we multiply the current by is R over L or 1 over L over R. And then the constant is Vs over L. For the capacitor, same format, but the constants are different. This is 1 over Rc, and this is Vs over Rc. So the equations are exactly the same format. So if we now find the general way to solve this equation in this format, then we can just substitute with the parameters and show or solve for I of t or solve for Vc of t with respect to time. See, that's the objective of the class. Because then if you have an equation of Vc of t with respect to time, in the case of the source, then you're charging the capacitor. How much time does it take to charge the capacitor to a certain voltage? You can plug in a certain value of voltage and solve for time. Or after a certain amount of time, what is the value of capacitor voltage? Right? It's either this or that. There is no other trick to it, really. Same thing with the inductor. Okay, so now we have to figure out how to go and review some of our math. So these are the forms of the equations, and again, if the sources are DC, if our batteries, if we're supplying this, charging this train or using a DC source, then Vs over Rc or Vs over L, which is the right-hand side, these are constants. Okay, so for now, let's assume that they're DC. We're not going to worry about AC systems. We're going to assume that they're DC sources, so these are constants on the right. Right? So these two equations are in the general form of dx of t plus ax of t equals b. Correct? This is the general form, and if we are able to solve for x of t, then I can solve RL circuits and RC circuits. Right? Because for the RC circuit, A is 1 over RC. For the RL circuit, A is R over L. For the RC circuit, B is Vs over Rc. For the RL circuit, B is Vs over L. And that's it. Right? So how do we solve this equation is what the core of what we need to do right now. So it should be a good review for you guys. Let's assume for a while that B is 0 for now. Okay? If B is 0, then we have an equation that looks like 4. Right? dx of t by dt plus ax of t is equal to 0. So I'll bring one of them on one side. Right? So what is x of t? Remember what the objective is to solve for x of t. So what is x of t? X of t is equal to its differential. Right? So what is a function that satisfies this condition? Exponential. If it's exponential and you differentiate it, it will be an exponential multiplied by a scalar, some number, right? So, but that's the function that will satisfy this. So if we have a 0, it's easy. It's easy because we know the solution to this case, the homogeneous differential equation will be nothing but the exponential form. Exponential form multiplied by a constant, right? So how about if we don't have a 0? If we don't have a 0, we have to satisfy the exponential still, right? So we envision that the solution will have this exponential multiplied by a constant, and then in the other case, the solution also includes some additional constant. So it's like a shift in level or of some kind, right? It's like having the exponential plus some constant value, right? So the general form for the solution of an equation in the format that we would like to solve, first order differential equation, will include an exponential component and a constant term. Right? That's the general form. So we will write the general solution as the general solution to this equation. Where is it? Here. Here. This will be the general form for x of t. Right? I skipped a lot, but because some of it is not very nice to explain. I mean, not easy to. I think the way I explained it is better than the slide. I hope. So the idea is to reach this general solution, right? And then we need to do what? Then we need to figure out what K1. How do we calculate K1, and how do we calculate K2, and what S is equal to. Right? So then we go back and do some of the substitutions. So if we go back to here, Yeah, let's go back to this one. This is the case where it's a homogeneous equation. The right hand side is 0. We said the solution to that is the exponential, right? So it's k2 e to the st. So we'd like to find what k2 is equal to and what s is equal to. That's one of the objectives that we have. So in that case, we need to go back and substitute in the original equation. So we said that x of t is equal to k2 e to the st. Our original equation looks like this: dx of t plus ax equals b. Or we're solving the one with 0 now. So dx of t plus ax equals 0. The solution to that is this k2 e to the minus st, right? So xc of t is this k2 e to the minus st. So we will substitute for x of c and differentiate it and substitute in this equation form, right? Because we know what x of t looks like in this case. So we put it in there. We also differentiate it and put it in here, and then equate it to 0, right? And then from the initial conditions of the circuit, you will be able to calculate k1 and k2, or k2 in this case. And similar thing we will do with k1, right? So we know that solution to this looks like a certain thing. We will substitute. So we know the solution looks like this. I go back and substitute in my equation. My equation was dx of t by dt plus a x of t is equal to 0. That was my equation. I took my solution format, I put it here, this is x of t, and I differentiated and I put it here, right? And then I have a new equation. This new equation, so I put it here and then I differentiate. So I differentiate this k2 e to the st with respect to time, and I get k2 s e to the st plus a k e to the st, right? So this is what I get. After getting this, I can reshuffle this around, take k2 e to the st as a common factor outside, and I'm left with s plus a is equal to 0, and multiplied by k2 e to the st. So one of these is 0, right? They multiply by each other, one of them is 0. So k2 e to the st is not 0, because that's actually the solution to our differential equation, right? So the x of t cannot, if this is 0, then x of t is 0, right? So, and we know that's not true. In the general case, it's not true. Maybe at a specific time, x is 0, x of t is 0, but in the general case, I cannot assume that. So in the general case, what we have is s plus a is equal to 0, or s is equal to minus a. So, and then a is equal to what? In each of these, in the RC circuit and in the RL circuit, we know the value of a. We go back to the equations. A in the RC circuit is 1 over RC. A in the RL circuit is R over L. Right? So I know A, I know S is equal to the A. So now, how do I find? So I know that the solution xc of t is equal to k2 e to the a, or the minus a times t. And a, I know what a is. I'm left with k2 that I don't know, and it's a constant that will be defined by the initial conditions of the circuit. Same thing with the b term. So we know that now our solution, we agree that our solution is a constant plus a constant multiplied by e to the st, and we figure out what s was, right? And now we continue and see what we can do from the initial conditions. So from the initial conditions, I want to be able to find k1 and k2. S is done. I just need to find k1 and k2 now. So from the initial conditions, I substituted t equals 0. This is k1 plus k2, right? k1 plus k2, then k2 is equal to what? X of 0 minus k1, right? And k1, we will see how we calculated k1 from a little bit before that. So k2 is equal to x of 0 minus k1. I will go back to the k1 calculation. And then if we don't, once we go back to this, we know that k2 is equal to x of 0 minus b over a. So let's see where they got the b over a from. Right? We know that when it was a homogeneous equation, the solution was the exponential. When we added the constant on the right hand side, we know that what this added was a constant, a shift to the exponential, right? Because x, the differentiation plus x of t, sorry, differentiation of x plus x multiplied by some constant is equal to a constant. If that constant on the right hand side is 0, x of t is equal to the exponential, right? If that constant on the right hand side is not 0, then x of t is equal to the exponential plus a constant, right? So the solution to the equation when we have a right hand side constant is basically that constant that we're looking for, k1. So we will assume that dk1 by dt, so the x of c, or the solution for x of t in the case where there is a constant on the right hand side, what it does is only add a constant to the solution. Right? So all it does is add a constant to the solution. And then we add the two solutions together, the k1 plus, so the solution to the equation without the right hand side term and the solution with the right hand side term. Right? So let me go back again. This is a general first order differential equation with a constant on the right hand side term. Right? The way that we solve it is this x of t in this case has a particular solution. They call it particular solution and complementary solution. Complementary solution is the easier one, right? Put a 0 on the right hand side, and the solution for x of t is a function that is equal to its differential multiplied by a constant value. So k2 e to the st, and we found s, and we found k2 in terms of k1. Where did k1 come from? K1 came from the fact that the particular solution of this differential equation is such that the x of t is going to equal its differential, bring this differential on the other side. It's going to equal its differential plus a constant, right? So I already know that from the particular solution that this function that satisfies this differential relationship between the solution and the differential is the exponential. So the general format of the solution for the equation was a constant plus the exponential function multiplied by a constant. Yeah. So what the particular solution adds is nothing but a constant to the full solution of the differential equation. So now I end up with x of t is equal to a constant. That's the particular solution, and then the complementary solution is the exponential. Adding them together is the solution to the full differential equation, the constant plus the exponential. So assuming that the particular solution adds nothing to the solution but a constant, then we'll call x particular of t is equal to a constant. We'll assume that, and we'll put it, and we'll figure out what k1 is equal to, and then plug it into the general solution, and then use the initial condition to see if we have satisfied everything that we have. So if x of t is k1, then plugging it back into the general equation that we have here. So dk1 by dt plus a times k1 equals b. So that's what we have here, dk1 by dt plus a k1 equals b. This is 0. The solution, k1 is a constant, right? So since k1 is a constant, then k1 is equal to b over a. Okay? So now I know what k1 is equal to. And it's a bit, I don't know, is everybody okay with what we said? Basically, we're assuming the solution will look like a certain thing. And then figuring out how to satisfy that by finding variables or values for k1 and k2. Right? So we found that k1 is equal to b over a, and k2 is equal to k, that's what we found here, k2 is equal to k of x of 0 minus b over a, where b and a and x of 0 is what we find from the initial condition. So x, if we're talking about inductor current, it's I of 0. If we're talking about capacitor voltage, it's X capacitor of 0, right? If we're talking, and then if we have an RL circuit, B over A is something defined by this. A for an RC circuit is 1 over RC. A for an RL circuit is R over L. B is Vs over RC. B is Vs over L. Okay, so now that we've gone through the math, we have everything summarized in this small table here. This small table is pretty much all you need, right? So as soon as you put your differential equation in this format, then the solution to the differential equation is k1 plus k2 e to the st. S is equal to minus a, which is this variable, this constant you have here. K1 is equal to b over a. K2 is equal to the initial condition of the variable x minus b over a. So this is really all you need to solve the RC circuits and the RL circuits. Now let's go and do some examples and try to put the RC and RL circuits in this differential equation format, and then apply this to them. So any questions about the logic? So this is the important part. Of course, even though I'm using a DC source that the Vs, we said Vs over this Vs over RL or something, Vs over RC here. It's Vs over RC and Vs over L. And we were drawing DC sources, right? If we are interested in steady state performance, what does that mean? That means that I've closed the switch in the circuit that we have. This is the circuit that we have. I closed this switch and I left it closed for a long time. Is that transient response? Remember, okay, the train example, right? As soon as the train comes into the station, I hook a voltage source or a power source to the train's capacitor and charge the capacitor. What happens after a while? The capacitor voltage rises until it equals what? Until it equals the source voltage. Remember, current will flow between two nodes if there's a voltage difference between them, right? So current will keep flowing from the voltage source into the capacitor as long as there's a voltage difference between them. And then at some point, capacitor voltage rises until it's equal to the source voltage. At that time, what happens? Will current flow? Current will no longer flow, right? So what does this make the capacitor look like? Fine, fully charged, but from a, is it going to be, it's an open circuit because current cannot flow, right? So it's going to make the capacitor look like an open circuit. How about for an inductor? And go back to the capacitor example. In this case, IC equals C dVc by dt. dVc by dt, there's no voltage change with respect to time anymore, so the current is equal to 0. Current is equal to 0, then it's an open circuit. Think of this when in the inductor example. VL is equal to L di by dt, right? So you have this inductor, not charged, connected to a source. Close the switch. What's going to happen? Current will flow until what? VL is equal to L di by dt, until the voltage of the inductor across the inductor is equal to the voltage from the source. At that time, current will no longer flow. Same thing. I mean, it's exactly the same, right? But let's see what's happening here. So VL in that case, there will be no current flowing. So VL is going to be what? VL will be 0. If the voltage across an element is 0, what does that element resemble? An open circuit or a short circuit? So current will flow, but what does this element represent? There's no variation in current, but what will this element represent? A what? A short circuit, right? If the current is not changing anymore, then it's a short circuit. Right? Remember, what does the inductor, like the water wheel? You push current through it, you push water through it, and what it does at the end is maintain a steady state flow rate. Inductor is the same thing. You try to push current through, you put voltage which pushes current. Inductors will resist current variation, but the current will vary slowly. until it reaches a certain steady state value, right? So and that's when the inductor is as if the water wheel is not there anymore, right? The water wheel is in steady state, flow rate is the same. So here it's the same thing. Inductor will, in this case, as if it's a short circuit. The voltage across it will be zero. It's like a short circuit. Current will flow. So inductors will look like an open circuit for a steady state source after a long time. But as soon as you switch it on, what's happening? As soon as you switch this switch on at t equals 0, you have a transient response, a period of transient response. Was current flowing before? Current was not flowing, right? As soon as you close the switch, current starts to flow, right? Current will start to flow according to this governing equation. So you solve this for I of t, there will be a governing solution for this current flowing through this circuit. After a certain period of time, this current will not change anymore, like the water wheel example, to reach a steady state value. If current is not changing anymore, voltage across the inductor is 0, so it looks like a short circuit. So how would you solve this circuit in steady state? Steady state, what's the steady state value of current in this circuit? It's equal to, what's the steady state value of current? Exactly. It's equal to Vs over R. So in steady state, this is a short circuit. And for the RC circuit, in steady state, this is an open circuit. I have an open circuit here. Here current does not flow anymore. Here current flows, but voltage is equal to 0. Here current does not flow, but voltage is equal to some value Vc, right? Because you've charged the capacitor to a certain voltage level. Okay, do you see the difference between capacitors and inductors? That's steady state. So in the transient, current will maybe start from 0 and then rise all the way until 100 volts divided by 50 ohms. That's the steady state value of current in this circuit. The V divided by this R. That's the steady state value. Current will not go beyond that. Right, so that's... So do you see the difference now between the steady state solution and the transient response? And if in the transient response, if this x of t I solve for inductor current or capacitor voltage, I put t equal infinity. What am I saying? I'm saying, what is the steady state solution? Right? I'm putting t equals infinity. So do you have to go and solve this system of equation? And you don't. You just have to make any capacitor open circuit, make any inductor short circuit, and divide d by r. Okay? So let's do some examples. So this is steady state, right? So this is a circuit, inductor, capacitor, resistor, all these complications, right? But they're asking you for the voltage and current for t very large, right? What does this mean? It means steady state solution. So take an inductor, put a short circuit. Take a capacitor, put an open circuit. So I end up with this simple circuit here, 2 resistors in series. What is the steady state value of current? 10 volts divided by 10 ohms, 1 amp. Right? What is the steady state value of Vx? It's 1 amp multiplied by 5 ohms, 5 volts. Right? That's all you have to do in this case. Same thing with this circuit. You have a current source here, and this in here, the current, I'm turning open the circuit. The switch is being opened at t equals 0. Right? So before t equals 0, it was closed. Right? It was closed. What was happening? The current flowing from this source was flowing in this short circuit. And now after I opened it, what's happening? Current flowing from this source will go into my RLC circuit combination. If I'm worried about the transient response, then this is a second order differential equation, a second order system. We will not solve these systems. right? I will typically, if you're given something like this, it's going to be you're asking for steady state solution. For steady state, VA, what's the value of voltage and current? What is VA? VA is the voltage here, and the current coming from current through this resistor. Okay, put the capacitors are open circuit, inductors are short circuit. I basically have this current source feeding my resistor. Do I have anything else? All I have is this current source feeding the resistor. So VA is equal to the current source, which is 2 amps, multiplied by 25 ohms, which is 50 volts. And IA is 2 amps, the current source. Okay? This was steady state. Let's look at solutions with RC circuits now. So I will not explain this, we explain this. Now let's go directly to this, to the example. We have an RC circuit here without a DC source, right? So without a DC source, the solution to that is only the exponential, right? So remember the K1 plus K2 e to the st? The K1 here is 0. There's no K1. We only have the K2. I think let's go to a numerical example. It will be very clear when we do a numerical example. Actually, this is before the numerical example. Okay, so I want to go back and write. So this is a case where we have 0 on the right hand side. So let's go back to the equation that box that we came up with before. In the case of the box that we came up with before, here, we said that x of t equals k1 plus k2 e to the s. Sorry. K1 plus K2 e to the st, and K1 equal to b over a, K2 equal to x of 0 minus b over a, and s is equal to minus a. And this is for the differential equation, so dx of t by dt plus a x of t equal to b. Okay, this is the general form that we have. Let's go to our example. Let's go to our example and apply it. Okay, so I have no source, so B is equal to what? Remember, for the RC circuits, the B is equal to Vs over RC. Right? If you go back to the differential equation that we had was d by dV by dt plus 1 over RC. This was the A, right? And this was the B, right? A d by dx by dt plus ax plus a equals to b. So b is equal to 0. So that this is my general solution. X of t equals k1 plus k2 e to the st. This will be my general solution. I go and see what k1 is equal to, what k2 is equal to. That's it. So b is equal to, in this case, I don't have a source, so b is equal to 0. That means k1 is equal to 0, and k2 is equal to initial condition x of 0 minus b over a. What's x of 0? What did they tell us here? That they told us that the capacitor was initially charged with some voltage Vi. This is the case where the train is leaving. You charge the train, they charge the train's capacitor, and the train wants to leave. So now that capacitor is charged to a certain initial voltage. They told you that. This is before VC of 0 minus, right? Before you turned on the switch, the capacitor was charged, right? It was charged to some value of voltage VI. So this is X of 0. And then minus, so we're trying to find, so X of 0. B over A is equal to what? B is equal to 0. So this B over A is equal to 0 as well. So what is K2 equal to? K2 is equal to VI. Right? So the solution now is X of t, K1 is 0, and K2 is VI, e to the st. S is equal to is 1 over RC. Minus 1 over RC. Sorry, yeah, minus 1 over RC. So S is equal to minus A. Right? So this is my final solution. Vc of t is equal to Vi, e to the minus 1 over RC times t. Right? So really all you need is these few terms. Same thing for the case where you have a source in the circuit. So let's look at what next example. This one. Yeah. This is the general solution. Why do you need to do it from scratch? I mean, it's good. I mean, you need to write this in this format: dx of t by dt plus a x of t equal to b. You have to write it. If you don't write it in this format, then you cannot use our A, B, C, D steps, right? Then you figure out how to solve it using first go back and do the differential equations and the way we derived it. You go and do the process again. But I don't think there is no need to do that, right? Now we've derived it, and we know that the general solution will always look at it like this. Then these are the constants in the general solution. You need to go back and figure out where it came from, right? But no, you don't need to. Every time you solve, no, you don't. Then let's see what the next example is. I think, yeah. So now here they just apply a few things. They tell you, okay, this is our solution. Okay, they sort of took the solution looked like Vi e to the minus 1 over RC times t, right? Minus 1 over RC times t. So they sort of grouped this R times C and called it tau, right? So, and rewrote it as minus T over tau instead of minus T over RC. And tau is called a time constant. So if T is equal to tau, then the solution, the capacitor voltage is equal to what? Vi e to the minus 1, right? Then e to the which means that e to the minus 1 is 0.368. So what does this mean? It means that after one time constant, after 1 tau, the voltage and the capacitor will be 0.368 times the initial voltage Vi, right? So the voltage has discharged to 36.8% its value after one time constant. So that's what they draw here. And they just tell you, okay, that the slope of this discharge waveform, if you extend the slope, it will intersect at this one time constant. They're just drawing it out there. And that at this one time constant, the voltage is equal to, the capacity is equal to 0.368, the initial voltage. Just an application of the equation. Same thing with, now that you have the voltage across the capacitor, what is the current through a capacitor? IC is equal to C dVc by dt. So if you have the voltage, differentiate that and you get the current through a capacitor. Now the voltage, differentiate that to get the current through a capacitor. That's all they're saying, that if you know this, then you know that, right? So you can just differentiate. And I think they do it for you here. No, here they do it with a source. They add a source to the previous circuit that we went through. Nothing changes. The only thing is, now we have what? Yeah, now we have a B. Now we have B existing, which means we have K1 and K2, exactly. But it's exactly, you just follow through the same. So K1 is equal to B over A. So after they wrote the equations, the Kirchhoff voltage law around the loop, they wrote the equation in the AX, dx by dt plus ax equals b sort of format. So this is your a and this is your b, and solution is x of t is equal to k1 plus k2 e to the st. K1 has a certain value and shape, K2 is a certain value and shape, depends on the initial condition. Then they gave you the initial condition. Assume that initially the capacitor is discharged, so the capacitor voltage is equal to 0. They gave you that, right? So K2 is equal to 0 minus B over A, so it's minus B over A. And the solution is the same. So you ended up with this solution. So I think this is, and then they draw the waveform, the same thing. So we'll just do another example or so next class, but basically this is RC and RL exactly the same. So next class I think we'll wrap up we'll do another example on RC, and then we'll also do the RL example exactly the same, believe me. It's just apply this K1 plus K2 e to the ST, write the differential equation form in the proper AX d by dt plus AX equals B, and then you just substitute. And you've done the RL and RC circuit. So we'll do more examples next time and continue.